Welcome to another GCBASIC tutorial for the PIC16F175 chip family. This is part 14, pulse width modulation, but I'm going to call it PWM quite a lot. So part 14, we're over the hill on the videos, we're getting there, we're getting to the end. Like this video, like the channel, like the list of tutorials and subscribe to the channel and etc. I'm in it for those. So we're going to use PWM many ways to dim the LEDs. It's representative of motors, etc. But that's what we're going to do. I don't normally show this screen. This is in the deck of slides. I don't show it because normally we don't need to sort of recap stuff like this. But look, this has got pulse width modulation with CCP and 16-bit resolution. Look. But I'm going to show you how you can do and generate PWM signals without using the modules that are inside of this microcontroller. Prereqs are that you've installed the software, you can program your chip, you've actually got that chip attached and the 4 LEDs are connected. And that's what this diagram shows you. I've got them on port C. No change there. Let's look at my board here, desk cam here. My board is here. Oh, you can see there's a signal on an oscilloscope, which I'll talk about in a moment. Down here we have an LED. There are 4 LEDs, and we'll be looking at all 4 LEDs through a flying lead into the edge of my board here, which connects me to my microcontroller. So I'm going to be connecting those quite a lot as we go through this tutorial. So back to the PowerPoint. So what we're doing is we're going to look at how we generate this type of signal. And this type of signal, sometimes we're going to change this, what's called the duty cycle. We might have a fixed frequency, we might change the frequency, but we're going to see different ways of generating signals that do this sort of shape, and we're going to see that shape of signal on the oscilloscope. Because PWM is essentially just a simple set of pulses, and it reduces the average power to the target device, be that an LED or be that a motor. And it's the average that actually then is effectively the load. And it then turns something faster or slower depending on how much of the duty cycle. The longer it is on, the more power. The average is greater, as in the diagram. In GCBASIC, we have many different ways of doing this, and I'm going to take you through the number that I've got. And that number I'm going to show you is about 7. Let me speak about this oscilloscope. I've got it on the board here. You've seen it, and I've given you the URL so that you can go and buy one of these on your own. It is the smallest oscilloscope I'm aware of. It's extremely functional. I had no problem with mine over the years. It's a fantastic little tool, and I've just got it hooked up. It's great, and we're going to see it working. So I've got 7 ways I'm going to show you. The simplest way is just to turn a port on and off. You can do that on any port, and this table lays out the different methods. The second way that you could do it is actually just pulse out on a port. Any port, doesn't matter. Third way is a thing that's called PWMOut. There are some cases where you need to send out a number of pulses, and we've written a macro that just does that for you. Any port. Then there's a fourth way called CCP, which is a module inside of the microcontroller. We're going to show you a fixed frequency, fixed duty method using timer 2. It's not important, it's all calculated for you, but you need to set the PPS. Low code impact, 2 constants, job done. So if you want to just generate a signal, you can turn it on and off. If you just want to generate a signal, very good way. But there's no CPU overload. There's no CPU load using that methodology. With the previous 3, you're going to have some CPU loading. I'm going to show you number 5, which is essentially the same as number 4, but using variable frequency, variable duty, using a timer. requires PPS, and the assembly does all the heavy lifting for you. You pass it a couple of parameters, and the heavy lifting is done for you. I'm going to show you pulse width modulation using a 16-bit module that's inside the microcontroller. Much wider range of capabilities, but we're going to show you how to set up the PPS, and we're going to show you the parameters. We can't show you all of those. There's just so many different ways in that option number 6. And then number 7, a traditional way that we've got using a timer to send a pulse out. You can do it on any port, doesn't require any PPS. So many ways, and I'm sure there are others. So let's walk through the examples and view the results on this X Mini Lab scope. So let me get started. I'm just going to bring up GC Studio, and I'm going to select the 16F175xx chip family. I'm just going to get rid of that because I like to talk you through it. On my desktop also, I am going to have my oscilloscope software. Let me show you that. How can I show you that? I can show you like this. Because I've got the LEDs, the oscilloscope, the PC software that comes from Gabtronics on the screen as well. So we've got some great stuff to see here. I'm just going to move the Gabtronics across a little bit out of the way. There we go. And let's get started. Control B, open up the Explorer. Example 240, and we're going to rip through these at some speed. Let me program that, and whilst it's programming, I'll talk you through it. Now, I have reset the chip. I powered it off. Why have I done that? Because if you have been playing with PPS beforehand and you do not reset it, nothing happens. But look, all that's happening here is that I am turning on and off the port RC0 for 10 milliseconds. And it is flashing every 10 milliseconds. If we look at if I look at the division on the horizontal division there on the oscilloscope is 10 milliseconds, and it's absolutely spot on, which is exactly what we need. Let's look at so 240 has now got all its files listed there. So I'm just going to come into here, Control F, .gcb, just show me the GCB files because I'm not interested in all the other stuff at the moment. Gone. Fantastic. 250. PulseOut. Now I'm not going to show you, the chip stuff now because we know all about that. We know all about the constants being set up and the ports being set as outputs. But if I want to pulse out on RC0 for 10 milliseconds, I use the PulseOut command. And I'm just going to zoom in a bit. Oh, there you go. Control B, Control J to get rid of the windows. Look. There we go. Do a loop, pulse out, RC0, 10 milliseconds, wait for 10 milliseconds. Do you know what it's going to do? It's probably going to generate a signal that looks just like the last one. But now you've got greater control. Why have you got greater control? Because the units there can be nanoseconds right the way through to hours. Very simple. The oscilloscope didn't make any change, but it has done the work. Control B. Demonstration 260. Pulse width PWMOut. Control B. Control J. This is going to send out 4 signals on a port. Where do I? So this is PWMOut on a number. Where does it get this number from? I'll show you that in a moment. And it's going to read in the oscilloscope, the potentiometer value, and we'll pass that. Let's have a look what it's doing. So we say on here, PW_out as a constant RC0, PW_out1, and you can have 4 of these. So you can actually generate signals and send out pulses. You can say, send out 4 pulses. You set it as an output, and the code works. And that is it. But it will generate a very different signal because you can have 4 of these operating independently of each other. And we're going to see it's sending out 4 signals. Well, we can see it on the oscilloscope. It's doing exactly what it should be doing. So you want to generate a really simple signal, that's the way to do it. Control J. I'm just going to get rid of that 260 by pressing there. There we go. Get rid of it. 270. 270 fixed mode pulse width modulation. Control B. Now, it doesn't look like there's much code in here. It says PWM on. Trust me, if that's all you put in your code, it would work if you have PPS set up. So let's have a look at what we got at the top. I've gone into PPS and I have selected CCP1 and I have attached it to all 4 of the LEDs. We'll see it operate and then we'll look at PPS, the tool. And all we're saying is that we have 2 constants. What's the frequency we want? Pulse PWM underscore frequency, and what duty do we want? 50%. Let's program that. We'll see the results. For some reason that failed to program. Don't know why. Pass. I just unplugged him. It was my error. There we go. So what we're expecting to see here is a very different signal out on the oscilloscope. Now that is 30. That will be Control J. Get rid of that. It will be 1 kilohertz. It will be. I absolutely guarantee it. Let me just change the oscilloscope so that you can see the signal being generated. That's 0.5 of a second division, and that's 0.5 of a signal. It's doing exactly as programmed. Now, what the advantage here is if I want to change the... Can you see that on the scope? No, you can't see it. You can see it on here, so I'm happy with that. You can see it there. I'm happy with that. If you wanted to change the duty cycle or the frequency, you just change these 2 constants. 55 to program it, and I'm expecting to see the frequency change, that's the time division, and the duty cycle. Exactly what it's doing. Look at that. It's doing exactly what's advertised. Here we go. I'm just setting, actually, well, I'll just do an auto on it. There you go. That's got it. That's just turned on the second channel. I'll just turn the second channel off. Change the position down here and just increase the gain so that you can see it. And if I wanted to change the duty, 50%, job done. Now, it is dependent upon PPS. Absolutely dependent. Nothing, you get no action, no PPS. And now I've just changed it back to 50%. I'm going to put this code back to 1 because this is demonstration code for you. So how did we set up the PPS? Function key F4. I'm so sorry. Function key F4, PPS tool. I might have to zoom in on this for you. My chip is selected. In here, in the peripheral output, I've got a long list of stuff. CCP1. And then I've added it on to RC0, that's where we're attached to, RC1, etc. RC3 through to RC3, and then I put that code inside of my program, and that attaches the CCP module to those ports. They are now in control. They are in control, and if you want to ensure that you've got rid of the PPS, set them to 0. We've seen that before. So, need to get rid of that. So we're going to use the PPS again in a moment. Shut that one down. Control B. Let's have a look at using example 280, and we're actually going to change the cycle depending upon the value of the potentiometer. Now, let's have a look at the code. Same PPS because I've attached CCCP1 to my 4 LEDs. But down here, all I'm saying is that I want to have greater flexibility. I want to be able to change the duty. I want to be able to change the frequency. And you use the command H, that's hardware, H, PWM. Then you put in the frequency. The channel, I'm so sorry, the channel, you can have up to 4 channels. We'll check with that in a moment. No, 2 channels on this particular chip. A frequency of 1, and the value, whatever it comes back as from the ADC, that's going to be 0 to 255, which is equivalent to 0 to 100%, and it will just scale it. Let's have a look what happens. Got my little thing here, look, ready to tweak it. It's programming it. If I rotate the potentiometer, we will see the oscilloscope change. Look at that. Let me just bring up and change the. There we go. Look, I only want that will do. That will do. That's good enough for military work. That's potentiometer fully off, sort of halfway round, fully on. Now there is some jitter in there, and that jitter is caused by the update cycle. I'm just showing you the general principle, and you can use another command called H PWM update to get rid of that jitter. But look, that's all the command is. It says H PWM, channel number, the frequency, and obviously you can change the frequency on the fly as well. And we're sending it a value, and that value is between 0 and 255, which equates to 0 to 100. Does the scaling for you. Wow, cool stuff. Example 290. Example 290 is different, but we're giving you an example so you can see what's happening. Let's look at the PPS to start with. The PPS looks extremely different because with pulse width modulation, you can have, there are 2 channels. They're both 16-bit, that gives you greater resolution and greater control. You can do synchronization across 4 signals. You can generate hybrid signals, etc. I'm just going to show you the basic operations, how to get it working. I've attached the 16-bit PWM1 to all 4 LEDs. Then I've given you the registers from the data sheet, how to set it up. Because down here, all I'm doing down here is I'm going to change the duty I'm going to change the period. I'm going to change the duty cycle in a loop. There you go. It's doing it as I'm sitting here. It's already programmed it. Let me just change the oscilloscope. Look at that. That is beautiful. And that is 16-bit resolution pulse width modulation, and it's ripping through at some speed. Let's look at the code that makes that work. Essentially, if you can accept that all these registers in here, I'll just Control J that, all these registers in here set up the 16-bit, I've documented it for you so you can have a look. All that's happening inside of the loop is, it's just saying, right, the PMW duty is between 0 and a value that's a constant, and then I turn on and off. I have to turn on and off, re-enable the signal. And as I change it with my 4 next loop, the pulse width modulation PWM duty variable, it's loaded into the correct registers, and then you just toggle it on and off. And the reason it's getting brighter and darker on the LEDs is because the 16-bit value is going up and down. By adding 1 in the next loop, it's going down by 1. So it's a step -1. And how does it know to do that? Well, this variable called PWM duty is an alias to two of the registers that control the pulse width modulation duty. So you can actually create a dimension, a variable, as a word, and you can point it at two registers, which means that you don't have the complexity because it's writing directly to the registers. So as you change the for next loop, the magic of the duty cycle changing occurs. 16-bit. Fantastic. Let me shut that down. Finally, I'm just going to use an interrupt to do something similar. Now, this one, let me go to the top. No PPS. Do it on any port. I'm going to do it on RC0. And essentially all this does, it initializes it with a timer and then goes through a loop just to see if the value is greater than its previous register, and it would sort of work it out what the signal should be. I want to show you a trick. So here it goes. Look, the speed that we're going to be sending out is 0 to 100, and it essentially the interrupt fires every couple of milliseconds, and it just sets the motor speed. It's really simple. It's really, really simple. However, watch this. Function key F5. We've got the 16-bit oscilloscope and program still working. We've got this new program that does not use any PPS, and we get no signal. No signal. Why is that? I mentioned this previously. PPS is controlling the output port. I unplug the power, resets the PPS back to 0. I plug it in, and voila, the signal being generated for a motor is working perfectly, no PPS. Don't have to go into the details of how this is working because I'm just showing you here that you can use a timer to generate a signal and you can control a motor from this. I will leave that with you for your own delight. Shut the windows down. Back to my desktop. Back to my PowerPoint. Right, the next tutorial is quite short. It's all about using timer. The timer called millis. We ported this from the Arduino type solution, and we can show you just very quickly how the millis works and some of the great things you can do with millis and its downsides. Enjoy.